A completely stationary top layer often hides a turbulent layer beneath. When the leading mode of a dynamical system is entirely static, it can mask violent mathematical complexity just one step down the spectrum. We are analyzing a specific numerical regime, twisted transfer operators computing over the Bird-map phase space, operating strictly across the interval from -3 to 3. This analysis tests a specific architecture. We use a discrete boundary grid and apply the WBA Kernel, positioned precisely inside the rigidity window, where the epsilon parameter ranges from 0.70 to 1.10. At the macro level, the continuous version of this system is mathematically sound. The foundational work in paper 37 proved this continuum bedrock. This system carries a certified bounded variation spectral gap of at least 0.6509. This is an absolute mathematical constraint of the continuum limit, completely independent of discrete finite-grid experiments. Because that spectral gap guarantees continuum stability, any volatility we uncover in the discrete approximations is purely a finite-grid structural phenomenon. It does not alter the underlying continuum reality. Previous research in this series, spanning papers 48 through 51, mapped out a discrete taxonomy of cells on this boundary grid at the epsilon 0.70 mark. That work revealed a coarse band anomaly. Across the entire parameter interval from epsilon 0.70 to 0.74, the leading invariant density proxy completely collapses. It reduces entirely to a literal single-cell delta spike. The mass profile compresses into one coordinate, leaving the rest flatlining at 0. This total stasis asks, has the entire discrete Ulam matrix become inert, or is this isolated to that leading mode? Paper 52 addresses this by probing the space immediately adjacent to the baseline, the previously unexamined microband from epsilon 0.700 to 0.710. To test this, we execute a high-resolution scan. We reduce the parameter step size tenfold to 1,000th and compute the eigenpairs across two massive discrete grids of 8,192 and 16,384 cells. By forcing this level of parameter resolution, we test the depth of the anomaly. We want to see if the total stasis holds across the spectrum or if subgrid complexity emerges beneath the frozen spike. To evaluate the operator spectrum, we track 4 precise metrics: the leading eigenpair, the subdominant second eigenpair, the gap proxy between their eigenvalues, and the geometric sign change count of the second mode. We begin with the leading eigenvector, extracted from the column-normalized Markov matrix P, computed across all 22 microband grid configurations. The cumulative mass widths for the 50th, 75th, and 90th percentiles all lock in at exactly one single cell. Furthermore, the top 1% mass fraction registers at a definitive 1.00000 at every single step across the microband. These identical measurements confirm that even at tenfold higher resolution, the leading eigenvector remains a completely anchored spike. It exhibits 0 parameter dependence. The invariant density proxy acts as a sharpened null. It is a maximally inert mode that reveals absolutely nothing about how the operator reacts to parameter shifts. In transfer operator theory, classical bounded variation estimates and Lasota-York inequalities dictate an expectation: the system's parameter dependence should be reasonably smooth. The frozen leading eigenvector trivially satisfies that expectation, but analyzing the subdominant spectrum, the second eigenpair, tells a completely different story. This chart shows the finite-grid gap proxy. The blue and orange lines track the distance between the first and second eigenvalues at the 2 grid resolutions, revealing intense structural volatility. Look at the sheer scale of the swings. At the 16,384 grid resolution, the gap proxy plummets to 0.150 at epsilon 0.706, and then violently spikes to 0.983 at epsilon 0.705. These extreme expansions and contractions of the eigenvalue gap are occurring over microscopic parameter steps of just 1,000th. Importantly, the local minima and maxima align almost perfectly between the 8,192 and 16,384 resolution lines. This cross-resolution consistency proves that the extreme gap oscillation is a genuine structural property of the discrete Ulam matrices. It is not a numerical artifact of a single grid. This massive volatility in the gap proxy shatters the expectation of smooth parameter interpolation. The operator itself is highly reactive, even if its leading mode is completely blind to it. The instability in the eigenvalues maps directly to the physical spatial geometry of that second eigenvector. While the first mode remains locked in a single cell, the absolute normalized mass of the second mode rapidly expands and contracts as the epsilon parameter steps forward. At the larger grid size, its 90th percentile support width fluctuates rapidly, dropping to a minimum of 2,524 cells before surging to a maximum of 8,250. This chart introduces the sign change count. This is our sharpest diagnostic tool for revealing the internal mixing geometry inside the raw signed second eigenvector. The dashed red line tracks an erratic structural shifting. At epsilon 0.706, the vector is broad but nearly sign definite, crossing 0 times. Just a few steps over at 0.701, it fractures into a highly oscillatory state with 89 distinct sign changes. At the smaller 8,192 grid resolution, the structural oscillation climbs even higher, hitting 225 changes across the spatial domain. The previous coarse band scan entirely missed this internal geometry. A step size of 0.01 collapsed this entire chaotic range into just 2 boundary points, hiding the structure in between. The second eigenvector operates as the dark matter of the operator. It harbors an intense, grid-sensitive geometric oscillation that independently drives the system's subdominant dynamics. This raises a specific technical question. Is the volatile geometry of the second mode simply a mathematical artifact, a structural shadow cast by the stationary leading spike? This chart compares the physical trajectories of the mass centers for both eigenvectors. The solid blue curve tracks the dominant spike. Meanwhile, the dashed orange curve shows the second mode wandering across the entire unit interval, independent of the leading mode's position. Because the leading spike is highly concentrated, tiny shifts in marginal mass cause wild swings in its computed center. The two modes do not track each other. The two eigenpairs are geometrically uncoupled. The subdominant mode possesses its own unique parameter-driven dynamic, completely separate from the stationary invariant density. The findings in this series carry uncompromising guardrails. These results are strictly finite grid phenomena, scoped exclusively to the executed numerical meshes. The intense geometric oscillation of the second eigenvector is documented here solely as a structural property of the discrete Ulam matrices at resolutions up to 16,384 cells. We make absolutely no claims regarding the existence or the bounded variation regularity of any corresponding subdominant eigenfunction in the continuum limit. Furthermore, the finite grid gap proxy is merely a discrete measurement tool. It does not alter, bound, or challenge the certified continuum spectral gap established in paper 37. But the discrete data provides a clear structural lesson for numerical analysis. Assuming an operator is totally stable simply because its leading invariant density remains frozen is a mathematical hazard. A coarse parameter scan can entirely obscure an operator's true reactivity. In discrete transfer operators, the absolute stasis of a leading mode can perfectly mask the oscillatory chaos driving the subdominant spectrum.